Okay, this is section 2.3 of the Pre-Calculus 11 Chapter 2 stuff. We're continuing our studies on trig. This one's probably one of the more difficult sections in this unit. It doesn't get difficult until probably about page 3. So, if you're thinking back to grade 10, you learned how to deal with right angle triangles. The question now is, how do you find lengths and missing angles of non-right triangles? Well, I've given you a non-right triangle here. It's triangle ABC, and I'm going to ask us to actually try to find different ways of writing an expression for the altitude of AB. Now, the altitude of AB in this example would be right here. So I'll call the altitude H, or the height. And if I ask you to go back to your SOHCAHTOA days, how could you write an expression for the altitude of AB? Well, if I've got angle A here, and I want this height H, and I know the side B, perhaps we can use the sine, or SOH, or the sine equals opposite over hypotenuse ratio. Sine of angle A in this case would be equal to the opposite side, which is the letter H, divided by the hypotenuse, which is the letter B. So that's one way of doing it. What's another way? How about taking angle B, perhaps, and let's say sine of B in this case would also be H over what again? Yes, it's its hypotenuse, and I guess that'd be the letter A. So two separate triangles, two separate ways of writing the ratios. I guess I'm trying to find the altitude AB, which means I want to solve for H. So let's go back to the one in red right now, the red triangle. So H equals to just B multiplied by sine A. And I guess the blue one, H is equal to A times sine B. And you're thinking, so what? Well, at least both of them equal to H now. So if they both equal each other, then I guess the left-hand sides equal each other. So B times sine A equals to A times sine B. And that's kind of interesting. Now it's just B's and A's. Math people will do one tricky thing right now, which is then to divide both sides by the side length of A times B. And they'll do that because of the following. Watch what happens if I now divide both of these things by AB. The B's divide out, so you're left with sine A over the side length of A, and that equals to sine B over the side length of B. Nice. So the ratio of the sine of angle A divided by its side length of A is the same thing as the ratio of the sine of angle B divided by its corresponding side of B. Okay, I'd like you to do the same thing in step number 2. I'm not going to say anything this time because I want you to try it out, but it's very similar to what I've done, and let's see what kind of expressions you get. So in step 2, I want you to write an expression for the altitude of CB. So I guess we're trying to find the altitude. So there's my right angle. Let's call this now capital H, making it different than the one in step 1. And I'm going to ask you to try to do the same thing. Okay, so pause the video right now, try it out yourself, then come back and take a look at the answers, and then we'll move on together. Remember, two different triangles. Two different right triangles. Just like before, solve for H. Just like before, make the two things equal to each other. B sine C, C sine B. Just like before, this time I'm going to ask you to divide by BC. Whoop. Whoop. And you're left with this lovely ratio. Sine C over side C equals sine B over side B. And since both of these equations equal sine b over b, we now have the following. So in a non-right angle triangle, by the way, oops, this picture should be in here. Sorry. In a non-right angle triangle, what you've just found is that sine of angle A divided by its corresponding side A is equal to the sine of angle B divided by its corresponding side B, which is also equal to sine of angle C divided by its corresponding side C. Ta-da! And this, ladies and gents, is called the Sine Law. By the way, some teachers or textbooks will reverse or reciprocate this, and instead of having sines on the top, they'll have the side lengths on the top. So I'll just quickly write that down here. It's not my preference, but you might see it in your textbooks, or your teacher might do that. So I'll write it down here for you as well. Okay. But once again, I prefer the one where the sines are on the top. Okay, ladies and gents, that's the main idea for today. Let's see if you can now apply them. So here we go, example number 1. I'm going to ask you to use the sine law, please, this time. Determine the length of JL. So the length of JL is this side down here. I'll just call that X to make it simpler. Now remember, the idea of sine law is you need to find the angle and its corresponding side. So for example here, the angle 20 corresponds to the side, 8 centimeters. I'm looking for this missing side here, X, so I need its corresponding angle, which is this one up here in K. Uh-oh, it's not there, but I know you know that angles in a triangle add up to 180, so angle K is just equal to 180, take away 20, take away 70, and if you do that, 180 minus 20, 160 minus 70, that's 90 degrees. So, using sine law now, and by the way, up here when I did the, I guess you would say formula definition, I use A over A, B over B, C over C. Doesn't matter what letters you actually use. Just remember that it's the corresponding side and the corresponding angle. So in this case, it's the angle K, which is 90 degrees. So I'm going to start writing this as sine 90. And its corresponding side length is my variable X. And this is equal to, I guess, my other corresponding pair, which would be sine of 20 degrees divided by its length that it corresponds to, or 8 centimeters. And here you have it. You don't need all 3 ratios in the sine law, you just need 2. So I like these 2 ratios. You can now go ahead and solve. Use it whichever way you wish. Most people like to use cross multiplication. If you want to, that's fine, as we have 2 equal fractions on the side. So cross multiplication says I could take X and I multiply it by sine of 20, and that's equal to those 2 things multiplied together, 8 times sine 90. You can also just isolate X, 8 times sine 90 divided by sine 20, and at this point I'll go to my lovely calculator and make sure you are in degree mode. Let me double check. Yes, I am. Thank goodness. So 8 times sine 90. We'll close the bracket, divide by sine 20 degrees, and lo and behold, you have your answer. 23 point, I'll round this to 1 decimal place. So 23.4. X equals to 23.4. And my units in this case is centimeters. Ta-da! Now you might be thinking, wasn't this a right triangle? And your answer is, you bet. Since this is 90 degrees, this is a right triangle. So you're like, why did we even use sine law? And I'll say, you're right. You didn't actually need to. You could have just thought about this as the right angle. This is the opposite side and all that kind of stuff. So we could have done the following. Sine of 20 degrees equals to the opposite, which is 8 over x, which is the hypotenuse. And you could just solve from here. X equals to 8 divided by sine 20. Well, I'm going to ask you to look at that and compare it with this. Are they the same? And your answer should be, because what is sine 90 from last day in section 2.2? You'll go back and figure it out. Okay? Or use your calculator. But the answer is 1. So they are the same. Okay? So what I'm saying is, you can actually use sine law for right triangles as well. So pretty much sine law replaces SOHCAHTOA. Goodbye, you can use sine law in most cases. Let's turn the page and let's try a few more examples, okay? Here's example number 2. I'm asking you this time to use Sine Law to find the missing angle. In this case, the angle I'm looking for is angle C. So once again, I'm going to try to look for C, and its corresponding side must be 12. Okay. Do I have another angle and its corresponding side? I sure do. I've got B and its side length of 15. So I think I'm set. I can start writing my ratios. I'll say sine of the 115 all over 15 is equal to the sine of my missing angle C. So I'll just use C divided by 12. Once again, it's two fractions, one on the left, one on the right. You can cross multiply to try to solve. So 12 times sine 115 equals 15 times sine of C. I'll actually ask you to isolate sine C first this time. So sine C is equal to 12 times sine 115 degrees all over 15. It's time to go ahead and use your trusty calculator. 12 times sine 115. Don't forget to close the brackets. And I got this 0.7250. So sine C is 0.7250. There's a few more decimal places, but I'll just keep it for now. Your goal is not to find sine C. I said find the measure of angle C to the nearest tenth. So what's my last step here to solve for C? You gotta get rid of the sine, and please don't say divide by sine. Sine's a function. We can't divide by that. What you want to do is you want to take the inverse of that function, or some people call it arcsine, or some people call it sine negative 1. Anyways, it's the inverse sine of that decimal. And so let me show you how to do it on your calculator. Second function sign. I'll just ask you to type in the decimal. If you don't want to type in the entire decimal, your graphing calculator has the thing called answer here. Second minus gives you answer. It will do the inverse of that decimal, 0.725, blah, blah, blah. And there's your answer, 46.47. I asked you to round this to the nearest degree. Oh, sorry, tenth of the degree. So 46.5. So from here, I'll say C equals to 46.5 degrees. Done. All right, so I showed you how to find the missing side length. I showed you how to find the missing angle. So I guess there's nothing more to show you. It's time for you to try some applications to this. So example 3 and 4 are two lovely applications. Perhaps I'll try 3 with you, and I'll give you some time to try 4. Okay? Okay, so in example 3, we're talking about a ferry starting at Benton, then going to Carr, and then ending its journey at Austin. So I guess you need to find these missing links. I'll call this X, I'll call this Y. And you're determining the distance the ferry must travel. That's, of course, X and Y. So I guess we should do that first, find X, and then we'll need to do the Y part next. And then ultimately, once we find those two answers, that's right, we just have to add them up. So, once again, how do we find X? Well, X to me is this, and its corresponding angle is given. That's great. So we can write the ratio, if you like, sine 43 degrees all over X, and this is equal to, well, we could use 62, but unfortunately there's a variable there of Y, and that's not going to help me right now with two variables, so don't use that. The only other length I do have is the 32, but then I'm missing the angle that's over here. Or am I? Because you do know two angles in a triangle, so you know that all three must add up to 180. If I took 180, subtracting 43, and then I subtract off 62, what do we get? 180 minus 43 minus 62. Bravo, 75 degrees. So we could then now say sine of 75 is divided by its corresponding sine of 32. Now we can solve this because there's only one variable. So go ahead, cross multiply and solve. Bring out your trusty calculator. Once again, make sure you are in degree mode because your angles are in degrees. 22.6. Okay. Kilometers. That's x. Alright. Your turn to solve for y yourself. I will be quiet. You stop the video. You try it. Once you got it, come back. We'll find the total distance and then we'll all be happy. By the way, if you're cheating and just waiting for me to do this, you won't learn as much as if you tried this on your own. Alright, 51.9. That's what I got. And if you got the same thing, yes, we are good to go. Good to go where? On to example 4. Alright, the Eiffel Tower in Paris, in France. I'm asking you to find the height. These two guys went on this trip. Daniel's at point D. He looks up, and to get to the top, he measures that it's 63 degrees from the horizontal. Edward is farther back, so he doesn't have to stretch his neck as much, but still looking up, 31 degrees. The question is, how high is the Eiffel Tower? So use your understanding of Sine Law to try to figure this out. You're like, I don't have any measurements. Yes, you do. It says the distance between the two men. That's this point right here. That's 346.4. So I guess what that means is we should be looking at this non-right triangle and trying to figure out what we can determine to help us solve for the height. I think we need another length. The question is, which length do you want to find out? Do you want to find dt? Or do you want to find et? And I guess once you find one of those lengths, then what do you do to help you find the height of the Eiffel Tower? Now, there are multiple ways of doing this question, so I'd like you to actually think about this on your own first. Okay, I've already given you a hint. I would say either find dt or et first, and then I guess my next hint to you would be, since the height is this length, and if I were to draw something like that, whoa, 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 do you see a right triangle? Ah, good old days of SOHCAHTOA. And by the way, that would be good for you if you used ET. But some of you don't like ET, because you don't want to go home. Get it? ET, go home, haha. Whatever. You might want to find DT and also still create a nice right angle triangle. And once again, SOHCAHTOA is at your disposal. Alright, ladies and gents, I've given you very good hints. It's your turn to try to do this. Okay? Alright. Stop the video, try it out, come back. By the way, this time my video answer will not be the full solution. Hahaha, you do have to think on your own. Okay, see you in a bit. I hope you're also not just copying everything I'm doing, because you don't really need to copy what I just said there, or ET, right? But I will show you the answer to DT. Haha. So, anyways, I'll just do DT. DT. Let's call that X then. The corresponding angle is 31. The 346, that's a problem because I need this angle up here. I don't have that. I'm in trouble. But I do know this angle here because angles on a line add up to 180. So 180 minus 63, that equals to 107, I believe. Oh, no, I'm not. I'm wrong. 117. Just checking. And then therefore, if that's the case, then this angle up here would be 180 minus 31 minus 117. Ooh, what's that? 180 minus 31. Oh boy, oh boy. 149, I think. Minus 117. I think that's actually 32 degrees. So sweet. Sine of 32 all over 346.4. That's the ratio you should have set up. If you did ET instead of sine 31, I'd say you'd have to use sine 117 over the length of ET. In this case, I went and solved for X, or in this case DT, and I got 336.67 meters. And then step 2 is to actually use the right angle triangle. And just use SOHCAHTOA. So let me just quickly draw out my right angle triangle. I want the height. This is 63, and this length is 336.67. So how about sine of 63 degrees, because I have the opposite side and the hypotenuse side. So sine 63 equals the length of the hypotenuse, length of the opposite divided by the length of the hypotenuse. And then I think you can just solve for h from here. Do I really need to tell you what the answer is? Do I really need to tell you what the answer is? I'll tell you, it's pretty close to 300. So 299.98, I believe. 299.98 meters. By the way, that actually might be the actual height of the Eiffel Tower. I don't know, but there's Google, so you can go check it out yourself. Cool. Whew, how are we feeling right now? So far so good, I hope. Alright, remember how I said it gets tricky on page 3? Well, guess what's next? Page 3. Oh, no more pictures. Boo-hoo. It's your job to try to draw out the picture yourself. Okay. And this one also says solve for angle C first, then solve for the entire triangle. What does it mean when I say solve for the entire triangle? Well, that just means you need to find out every single missing piece of information. Missing angles and all the missing sides. I think our first challenge here is to actually draw what we actually see or read in triangle ABC. Okay, angle B is 70, so I'm going to try to draw this as accurate as I can. Let's call A up there. Let's call B down here, and I guess C is over here somewhere. Angle B is 70. All right. Length AC is 14.1, so that's actually the corresponding side of angle B. And AB, that's, I guess, the side length C, is it? Yeah, I guess so. That's 14.5. All right. So the angle says solve for angle C first, and then solve the entire triangle. Okay, so I'm going to ask you to set up the ratio. You should be able to do that. Go ahead yourself and try that now. So I hope this idea of setting up the ratios is pretty straightforward now. Just find the corresponding side and match it up with the corresponding angle, sine of the angle over the side length. Okay, cross multiply. So, what do we have here? 14.1 sine C equals 14.5 sine 70. We'll do sine C 14.5 over sine 70 over 14.1. Let's do this calculation here. 14.5 times sine 70 divided by 14.1. Got 0.9664. 0.9664. That equals to sine C. So C is just the inverse sine of 0.9664. And let's bring out my calculator again. Ta-da! 75 degrees. Cool. So I know that angle C is 75 degrees. Let's go back to my drawing now. Since this is 75, that's great. I can now go back and now solve the entire triangle. So by solving, I need to find out the other missing angle. How about angle A up top? So that'll be 180 minus 70 minus 75. That'll be 1 and 10, 75. That's 35. I think so. And then now, since I know that, I can find out the missing length, which is this one down here. I'll just call that little a. So sine of 35 over little a equals sine of, doesn't matter which one you use, I'll just use sine 70 over 14.1. You could have also done 75 and 14.5. It doesn't matter. Go ahead and do this on your own. Alright, I think the answer is 8.6. 8.6 cm. Nice. Cool, we're done. But I still have so much room. Remember how things are supposed to be connected? I want you to think back to section 2.2, okay? That was, I think, last day's lesson, so I hope you did your homework. When you do a question like this, that I'm going to circle right here, sine C equals 0.9664, you do the inverse sine. From last day, I hope you remembered that when the sine ratio is positive, you actually have potentially two different answers. They could be in, remember, first quadrant, where all the angles are positive. So I think in here, what you just told me was that angle was 75 degrees. That's corresponding to this answer of C equals 75. But where else can sine be positive? That is right, in quadrant 2. So if I were to draw my axes again, x and y, like this, you could potentially have an angle over here in quadrant 2, because all students take calculus also work here. Remember, they share the same reference angle of 75. So what's the measurement here going to be? 180 minus 75. What you have now told me is C equals 75, or C could also have been equal to 105 degrees. You're like, what? In this example, there are actually two different triangles that you can draw based on this scenario of information. So you're like, what? How can it be 105? Well, let me try to draw it for you here. So once again, we have A, B, and this is 70, and this is 14.5. And remember before we had the angle or the side like this, 14.1? Well, what we're going to do is going to take this side here, cross it out. We're actually going to take it and swing it over, whoop, over here. I guess we'll have to cross that part out. And then we can now say that this angle, which is angle C, is 105, and that this length is 14.1. So in essence, we took that side length AC, and then we swung it over. Instead of having an acute angle of 75, we now have an obtuse angle of 105. So our triangle in question now is actually an obtuse triangle like this. Trippy. And so I guess in that case we have to do the whole process again. Now we'll have to find out this angle A. Angle A is just 180 minus 70 minus 105 this time. That's a measly 5 degrees. And then to find out side length A, we'll do the same calculations again. Sine of this time 5 degrees over little a equals sine of 70 over 14.1. Do your cross multiplication business and get A in this case. What do we have here? 14.1 times sine of 5 divided by sine of 70. Whoa, measly 1.3 centimeters. But also correct. So, what in the world just happened here? Let me look at the example above. You were actually given two sides and an angle, but notice where this angle is in relation to the two sides. I'm going to use my purple pen here. The angle is there, and the sides are outside there. So the angle is actually not between the two sides, it's outside the two sides. Or we call this an SSA triangle, a side, and then an angle that's outside of those two sides. Okay? When you have this type of scenario, sometimes you'll get what we call the ambiguous case, and that's what we just had in the previous example. You actually have two different triangles that can exist, or it may occur. Now, usually in these questions, you have the measure of a side length B, that's the first side length. You also know the measure of an angle, that's angle A, and you have one more side length, I guess that's little a, that corresponds to angle A. And these three things can be used to calculate if you actually have ambiguous case. You don't always have an ambiguous case, and this is shown, by the way, because in example number 2, we also had side angle, but notice in this case the angle was 115, so when we did this we knew that there was only one angle that was acute. But the question is, when do we know if we have this ambiguous case? And let me try to show you. So, when, by the way, you should start it. This only happens in this case of side angle. When you have this, okay, let's say we know for sure angle A. So this is angle A down here. And then this is what we call side B. Okay. We're going to create another side length A. I'll use black, and A will be this length here. So this is, don't worry about the circle around it. It's just showing you that the length of side A can change. So notice the length of side A in this case is here. The length of side A in this case is over there. And the length of side A in this case over here is over there. Okay? So back to the one on the left. Notice that in this case, I want you to compare A with H. H is the height. So the height of the triangle. Okay, that's H. In this particular case, the A is less than H. So the length of A is less than the height of a right triangle that can be created. In this case, then, therefore, you don't even get a triangle. So no triangle in this case. Okay. We'll leave that blank for a sec. We'll come back to it, okay? Looking at the next one, A equals to H. So notice that the length of A now is equal to the height. And if that's the case, the triangle you get, of course, is one of them. But I'll even make it more specific. One right triangle. And that's, of course, when the length of A equals to the height. Here's the interesting case. Notice here I'm saying the length of A is bigger than the height. So once again, here's bigger than the height. And can you see that circle? That's kind of like a radius, so that A value is longer than H. But notice also that this A value is not more than the length of B. And in this particular example, this is where you get your two triangles, or the ambiguous case. I can't spell. So this is where side length A is smaller than the other side length B, and also larger than the height H. And once again, in our previous example here, this is where the A swung over to the other side here. So then instead of having one larger triangle with all three angles that are acute, you now can produce a smaller triangle over here where one of the angles is obtuse or larger than 90. The final one, well, that's where A is bigger than B, and that's where you're going to only get one, and I'll say one non-right angle triangle. And that's like example number 2 on page 2. Okay? Now, I did have a blank here I didn't deal with yet. Sometimes people don't want to always say H, because that's something else, some third variable. So how does H, B, and sine A relate to each other? Well, let me just quickly draw something for you. Here, once again, is angle A. H is, once again, the height. B is the side right there. And if I asked you to find me a relationship connecting all these three things, you would say from your SOHCAHTOA days, sine A equals to H over B. And if I actually ask you to solve for H, then H equals to B times sine A. So many textbooks will now ask you, instead of using the letter H, to replace H with B sine A. So back over here on the one on the left, if A is less than B times sine A, then you have no triangle. If A is actually equal to the length of B times sine A, so once again, you're looking at this as B, so you know the length B, you know the angle A. If you do B times sine A, and that equals to that third side, or sorry, not the third side, the other known side, then you get one triangle. And here, if B times sine A is less than little a, which is also less than little b, then this is the ambiguous case. So this is the one that a lot of people will have problems with, but I want you to understand and know. B times sine A, okay? A and B. If you calculate all those things and you get this situation, you got the ambiguous case. All right, like I said, this is the hardest part, okay? Many people, when they deal with the SSA situation, they will be able to calculate things, but they forget about a possible second solution. All right, one more example here, and then we're done for today. So here's section 2.3, last example. Two students are holding tethers, so that's like the string, to a helium-filled balloon. So let me just quickly draw my balloon. Here's my balloon. Woo! String, okay, that is floating directly above the line through the student's feet. No, it's not feet, it should be feet. So what I'm saying is the two students are standing on the ground horizontally like that. Andrea, let's put her over here. She has a tether that's 25 meters long and an angle of inclination of 45. Camille is over here. Her tether is 20 meters long, a little bit shorter. And the question is, to the nearest meter, determine the distance between Andrea and Camille. So I'm going to ask you to find this distance here, x. All right. Now, if you're blindly trying to do this, you're like, I don't know. Well, once again, you just have to go ahead and use sine law. But wait, what type of triangle do we have here? Notice we have an angle, a side, and a side. ASS, oops, that's a bad word, so flip it around, SSA. So notice this is an SSA triangle, so you should really check for the ambiguous case first, okay? And to check to see if you have the ambiguous case, remember we have to calculate a few things. You need to then calculate B times sine A, and then you want to compare that with side A and also side B. So I guess in my example here, 20, since that's across from angle A, I guess that's A. What's my B value? It's the other side that I know, so I'll call that my B value. And then you'll be confused, you're like, but that's a C. Well, you can call that the angle B, it doesn't really matter, okay, but that's just your other side. So now let me do these calculations. B times sine A will be 25 times sine 45. What's that? What's 25 times sine 45? That's 17.7, okay. And then compare that with A and B. A is 20, B is 25. So I guess if I were to compare these things, I'm saying 17.7 is the smallest, A is in the middle, and B is the longest. I guess I should write down 20, which then means I have this scenario. B sine A is smaller than A, which is smaller than B. And this scenario is what on the previous page? It looks like it's right here. Yes, this is therefore the scenario that means, therefore, this is the ambiguous case. And therefore, you need to solve for two triangles. Or there are two possibilities. So, here's my first one. I'll do the calculations. Now, sine 45 over 20 equals to, I guess you need to find angle B first down here, or angle theta. So I'll say sine theta over 25. Once again, we'll do the cross multiplication. We'll try to solve for angle theta first. Times sine 45 divided by 20.884. And then if I want to find the angle, it's inverse sine again. And there we go, 62.1. So theta here equals to 62.1 degrees. Or, remember, once again, what could this be? All students take calculus. I'm asking you for this angle, which is in the second quadrant. The reference angle is 62.1. So 180 minus 62.1, 117.9. So theta could be 117.9 as well. So that picture would be one like this, and I'll quickly draw it for you. 25, 25, and then now I guess my angle theta is here. 117.9. This is still 20, and you can solve for x in that sense as well. Okay, so once again, ladies and gents, two situations. And by the way, I only found out the angle, so you still need to solve for x, so why don't you go ahead and try that. The black situation, I will set the ratio for you. Sine now, I can use 62.1 divided by 25 equals to something over x. That something is this missing angle, so I guess the missing angle, let's call that angle, I don't know, dagger. Okay, so we'll go dagger equals to 180 minus 45 minus 62.1. That's 135 minus 62.1. How about 72.9? So sine 72.9. Okay. You go ahead and solve this, get the answer, then do the same thing with the other one, get the answer, and there you have it. You'll have two distances, and you'll have solved the problem. Okay, I'm tired. You should finish this off yourself. Okay? Do that now.